If I had a glass of water, or just a glass, and if I have some sort of tap that we pouring in water, do that, and then it starts filling up this cup, this container here, and what I want to know is let's assume that, well, actually it doesn't really matter because it's not really important, but what I want to figure out is how fast is the volume of the water here increasing at any point in time. So the way we would try to figure out how fast it's going at any instant of time, one of the tools we might use is that, I don't know if I can change it there, is that of calculus. So calculus is essentially built off of the foundational question of how is something changing at any instant of time. And it calculus is really built off of as well other math topics that you learned in algebra 2 and pre-calc. Because I'm gonna be honest here, algebra 2 and pre-calculus, the concepts you learn in these courses, you're pretty much never going to use any of them in real life unless you're using it with calculus. So you're pretty much never gonna use the concepts of algebra 2 or pre-calc on their own. Typically, you would use these topics to solve a problem that typically involves change. So you would need calculus along with a combination of these topics. So I'm gonna be honest. Uh, calculus is pretty much just the application of what you learn in algebra 2 and pre-calculus. But essentially, calculus is really just a way of understanding and modeling dynamic change. So, if we look at an example, if I were to graph some sort of motion like that, maybe that's the motion of a particle, and here you have your position axis, and this is, I can't really think to that. Oh, I will do. And this is your time axis. And what I want to figure out is, first of all, let's try to see what is the average rate of change for this entire function. And you'll see what I'm trying to get at in just a minute. So the average rate of change for the entire domain would be the slope of this line over here that connects I guess you could say the bottom boundary of the domain and the upper boundary of the domain. So the slope of this line over here would be, well, it would be, let's just call this point over here the F. Actually, I'm just gonna say F. Maybe this is, I'll just call you D axis and you use your T axis. So here's your point at D is equal to 2F, and here is the point uh I. Actually, not I, because complex numbers. This is N for initial, because I wanted to do initial, but I don't want to use the I. So I'll just go with N. So this is D is equal to N and D is equal to F. The average rate of change of this over here would be df, not df, d of f minus d of n over f minus n. So if you know the values of f, n, and ut, well, actually, no, wait, no, that doesn't really work, does it? Oh, I think I confused it. No, you're supposed to go on the time axis. Oops. Alright, delete that without doing that. Alright, so this should be f, and this should be n. So we have d of f. Because I wanted to define this. I wanted to define like the actual t-axis, but I accidentally put it in the wrong axis. So you have d of f minus d of n over f minus n, and that will give you the slope, essentially the slope of this line that connects the bottom boundary of the function and the upper boundary of the function. Now, an interesting question is, or a more interesting one, is what if we didn't want to do the entire domain? What if we just wanted to do it from this point to this point? Well, it's the same idea, and this time we're going to define this point. We can do that as well. Um, six and no, I'm using that. What? I don't know. Just use x, and then over here, I'll call that point y. Then our average rate of change would, same idea, just be d of x minus d of y over x minus y. And I can do that because, well, my vertical axis is d, not y, and I have t here, not x. So it's completely valid points to name it. So the interesting question, especially when it comes to in the context of calculus, is, and it's gonna start getting bad if I just keep seeing the same colors. What if I wanted to find the rate of change of this instant, just this one single point over here? Well, what if we try to use the same logic over here, and let's call this point z. Then this would be what? So this would be d of, so we're not really having any change in the vertical direction. So over here we had d of f, and we were finding the average change of that to d of n. And same thing with this one over here, because with those d of y and d of x. But here we're not moving; it's just a single point. So we could just do d of z, and then we don't have really any other second point. So we could just d of z minus d of z. And then from that, again, some idea, we're not really moving, we're just a single point, so our x, or our t value rather, is just always going to be z. So we could do z minus z, which is equal to what? Well, d of z minus d of z is going to be 0, and z minus z is going to be 0. So here we're running into a problem of dividing by 0. So how would we actually figure out the rate of change of this point if we were to plug this into the rate of change formula? Change in let's generally change in d over change in t, right? So changing your changing your output over your changing your input. Well, I'm gonna get 0 over 0 here if you were to plug it in into this formula. So one way to think about this point here is, what if we were to take the slope of, for example, this line over here? We will calculate this average rate of change, and you'll say, okay, well, we got that. Now, what if we were to find the average rate of change over this interval here? I should probably use this smaller stroke with that. So much better. We could do that. We can calculate the average rate of change and say, okay, well, we got that, and then we can do it again over this interval, which would connect this point and this point. And so you can do that and you say, okay, so we got that. So what is this actually doing for us? Well, we can kind of see where that as we keep decreasing the interval, the width, or the interval, I guess you could say, of the rate of change at that instant is being approached as you keep decreasing the interval of your average rate of change. So if you were to somehow get this interval to be infinitesimally small, you could possibly calculate the rate of change at that instant. So, and this sort of idea of you approaching the rate of change at that instant is the idea of a limit. And the way you would write this out is that the limit of the, and I'm just gonna use C. I'm gonna use I here C for instantaneous rate of change, because we dealt with average rate of change ARC. So the rate of change at an instant, I'm just going to call IRC, instantaneous rate of change. The limit of the instantaneous rate of change as the interval of the average rate of change decreases, or the limit of the IRC as the interval of the ARC decreases is, wait, hold on, let's see, the limit of the instantaneous rate of change, well, actually this should be ARC, that'll make more sense, the average rate of change. So the limit of the average rate of change as the interval of the average rate of change decreases is equal to the average, or the instantaneous rate of change. So this over here is essentially the foundation for instantaneous rate of change. The limit of the ARC as the interval of the ARC decreases is equal to the IRC. So what this basically means is if I wanted to take an interval, let's say 5, 6, and I wanted to find the IRC at x is equal to 5.5. So again, I won't be able to just jump straight into 5.5 because that's just gonna lead me to 0 over 0 if you plug it into the formula. So instead of that, what if we just take another interval like 5.4, 5.6, and then we take the interval 5.49, 5.51, and we're essentially trying to simulate getting infinitesimally close to 5.5. So to the point where the interval of the average rate of change is so small that it's almost the interval of the actual instantaneous rate of change. Obviously, the interval would be 0, but we can't have an interval of 0 because 0 over 0 over here. An interval of 0 over 0 leaves us with a 0 in the denominator. So if you just keep doing this and you just keep you keep decreasing the width of your interval, and you keep zooming in essentially at the x is equal to 5.5, then you will be able to find the actual instantaneous rate of change at this point, or in this case at x is equal to 5.5. So how do we actually do that? Well, to figure out how to do that, we do need to learn some couple of concepts really about we're gonna learn more about limits, and we're gonna be able to actually define what instantaneous rate of change is in terms of a limit. This is really just a verbal definition, but how do we actually write this with mathematically, and then how do we actually deal with that mathematically? Because this is really just gonna get us so far. This is really just gonna be an approximation, or it's really just gonna be an estimate. So we can be talking about a lot more about the limit, and once we actually figure out because we're gonna learn how to actually figure out the instantaneous rate of change very early, but calculus isn't just about figure out the instantaneous rate of change and then boom, you're done. We're also gonna learn a lot more applications of using calculus, and knowing the rate of change at an instant, how can you apply that in certain situations?